Okay, welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from the Electrical Engineering Department at IIT Hyderabad. So, before proceeding with today's class, let's have a brief recap of what we were studying the last time around. In the last class, we built up the entire picture of how neural networks work, starting from one artificial neuron and then scaling it up to a full-blown neural network. A single neuron multiplies each input that it receives by a corresponding weight, then adds a bias and sums all of them up. This was called the vector matrix multiplication operation, or even the multiply and accumulate operation. This MAC operation product is then passed through a nonlinear activation function. When we scale this up to a network, we saw that we have your input layer and you have your hidden layer and you have your output layer. So the objective of the input layer is to bring in the raw data. We saw as an example, a 20 cross 30 image gives 600 input neurons, and if you have a color image, it will be just multiplied by 3. So each of these inputs were connected to the neuron in the next layer via weights which act like synapses. The hidden layers were the workhorses of your ANN, and layer after layer they compute these weighted sums and make them pass through activation functions, and progressively they start learning abstract features. Okay. Also, we saw that where most of the power consumption and computational intensity comes in ANNs is from this vector matrix multiplication. We saw the matrix form of it, y is equal to w dot x. Y was the output of that particular layer, w was the corresponding weight matrix, and x was your input data. Finally, we also looked at some of the activation functions such as sigmoid, tanh, and ReLU. Remember, we need this non-linearity so that these stack layers don't become just like one big linear regression map. Without these non-linear activation functions, you cannot really learn very complex data. And we also saw that ReLU is one of the most popular non-linear activation function, and we will see what is the reason for that. Okay. Finally, as you see in this image, we saw that training a neural network is like training a baby. What you essentially do is you point at the particular object. You feed the input, which is coming from a training data set, into the input layer. You also tell it what class this belongs to. You tell it the ground truth, as you see. This is the ground truth 100, indicating it belongs to the first class. And then you do your feed forward series of vector matrix multiplications, which gives you your predicted output. Using the cost function, you calculate how far is your network from the predicted data, and by tuning the weights throughout the network, you ensure that the cost function is minimized, and that is essentially the backpropagation algorithm. Now, since backpropagation is central to the operation of neural networks, today we will do a little bit of deep dive into backpropagation. So, to understand how backpropagation works, let us look at a very simple example. Let's look at a neural network just with one weight, simplest system. So what we have in these two graphs is the representation of your cost function versus the weight. Okay, as you can see from this blue line, it shows some parabolic behavior, near parabolic behavior, and currently in the entire weight space, I am at the point that I have indicated by this dot, and the objective finally is to minimize the cost function. How do you minimize the cost function? You make tiny changes to the weight such that you reach your objective. Objective is to minimize the cost function, which is your blue curve with respect to weight. So now the question asks, so if we are standing somewhere on this curve of cost function versus weight, how do we kind of move downhill? How do we reach the local maxima, if not the global maxima. And the answer, as you can see from this diagram and this red line, is the slope or the gradient of the curve. So as you can see on the top image, if the slope is negative, it is slanting downwards. See, if it is slanting downwards, the update to the weight is positive. What I mean is that the next iteration weight will be more than the current weight, as you can see over here. However, as you can see in the image below, that if the gradient of the slope is positive, then the weight update is negative. So what did I essentially say? That the direction of update of the weight is opposite to the direction of your slope. Why is this the case? This is because the gradient of any function tells you the steepest direction of increase, but we want to minimize. So we need to look at the steepest direction of decrease. And that is why the updated weight is equal to the original weight minus the gradient. And because it is in the opposite direction of the gradient, because gradient points to maximum slope, maximum change, so you want to go towards the local minima. That is why, because it is opposite to the gradient, this algorithm of finding out the updated weight is also called the gradient descent algorithm. Okay. Also, an important point to note is that when the weight changes, how proportional is it to the gradient? And that is also important to learn, that what is the size of each step when you move from the ith iteration to i+1th iteration. And that is controlled by something called the learning rate. So if the learning rate is too tiny, then what will happen? To come from this position to the local minima, you will take many iterations and your learning will be painfully slow. However, if this learning rate is very large, what you will keep doing is you will just keep bouncing off the negative gradient and the positive gradient without ever converging to the local minima. Therefore, the learning rate has to be very carefully optimized. So to summarize, we compute the gradient of the loss function with respect to the weights. See, gradient of the lost function with respect to weights, and then update the weights in the opposite direction of the gradient by the scaled learning rate. And when you repeat this process again and again, it brings your weights to that local minima where your error is the least. And this is the process which is known as the gradient descent algorithm. Now, how is this gradient descent algorithm actually applied in a neural network is what we will see. And that is the fundamental of backpropagation. And we will see backpropagation in action with a very simple example. Remember the simple neural network that we studied in the last class? What we will do is we will consider a bunch of neurons, only one slice of neurons in this complicated neural network. And we will see through the shaded region where there are only two hidden neurons between the input and the output, what happens in the gradient descent algorithm. Okay, so as we just discussed, our problem is now reduced to just two neurons which are connected sequentially or in series. And in this diagram, we just have two layers. In the first layer, we have the first neuron, which is computing Z1. Z1 is nothing but the product coming from the VMM or the MAC operation. And when you apply this output from the VMM or the MAC operation to the activation function, you get the value A1. Similarly, the second neuron takes the value A1, computes Z2 and applies its activation and outputs A2. Okay. So finally, what happens is your A2, as you can see over here, the A2 is giving rise to the predicted value Y dash. And this is where the backpropagation algorithm comes in. But to understand that, first let's define the cost function, which essentially measures the error between the predicted output Y dash and the true label Y actual or the ground truth. So what is our objective? Our objective essentially is to slightly adjust these two weights in the system, W1 and W2, so that this cost is minimized. How do we go ahead and do that? So first, let's focus on the weight of the first layer, W1. To find out what is the update to the weight W1, what we need to find essentially is what is the derivative of the cost function with respect to W1, or how does the cost change with respect to weight W1. But however, you have to notice that the cost doesn't directly depend on W1. The cost depends on Y dash, which in turn depends on A2, which depends on Z2, which then again in turn depends on A1, which finally then depends on W1. So in order to connect C back to W1, what we have to do is we have to use something called the chain rule of differentiation, which we may have studied in our basic mathematics courses. So as I have represented here, dou C by dou W1 by the chain rule. First, I will split it into Z2, dou C by dou Z2 multiplied by dou Z2 by dou W1. Further, to bring in A2 into the picture, I will write it as dou C by dou A2 multiplied by dou A2 by dou Z2 multiplied by dou Z2 by dou W1. So each term, if you see over here, is basically indicating how one quantity changes with respect to the one before it. See, C is depending only on A2, whereas A2 depends on Z2, and finally Z2 depends on W1. And multiplying all of them together links the output error C all the way back to the weight W1. And that is why these red arrows that you see in our particular diagram show that the error is actually propagating or flowing backwards. This is where the word backpropagation comes from. So first, we have to look at the cost to A2, dou C by dou A2. Next, we have to look at A2 and then from A2 to earlier quantities, and finally we move back to W1. So the essence of backpropagation is that the chain rule lets us push or propagate the error backwards throughout the network, layer by layer, so that we can compute the gradient for each and every weight. So in essence, the simple chain rule that we study in our basic calculus courses is what essentially makes learning possible in these deep neural networks in a very systematized manner. Now, within the chain rule, looking at the individual terms gives us a lot of insight. So first, let's focus on this middle term, which is dou A2 by dou Z2. Remember, you get A when you apply the activation function f on Z. So if you are taking dou A2 by dou Z2, it is nothing. It is simply the activation function of output neuron 2. Z2 is the weighted sum. So dou A2 by dou Z2 is nothing but the derivative of your activation function. Why is this very important? Why am I mentioning the second term? This is because during backpropagation, we need to see how changes in the weighted sum Z2 are affected by the activated output A2. This also tells us how sensitive the neuron's output is to the changes from its corresponding input. And this sensitivity is what is controlled entirely by the activation function. And this is why choosing an activation function whose derivative is simple and well behaved is absolutely critical for deep learning. If the derivative vanishes, like in sigmoid at the extremes, and gradients disappears, the learning will absolutely stall. If it explodes, the training becomes very volatile and unstable. That's why functions like ReLU have become so popular, because their derivatives are simple and they avoid vanishing. So in this middle term, the derivative of the activation function is the key to make backpropagation work in principle. So we have to select this activation function very, very carefully. Next, we look at the first term, The first term, as you can see, is dou C by dou A2. If you expand out dou C by dou A2, it is nothing but dou G, where G I have just approximated to be the cost function, y minus y dash by dou A2. And within y dash, which is the computed value, you see that it will then in turn depend on A2 and W2. So by checking dou C by dou A2, basically we are saying that in order to first find out W1, you need to find out what is dou C by dou W2. And this essentially furthermore emphasizes the idea that errors propagate backwards, and this is the principle of backpropagation. Finally, we look at the second step of operation of a artificial neural network. Now your trained dragon is ready to spit fire. What this simply means is that in the subsequent phase where the model is completely trained, it is deployed to make predictions on completely new data. New data means data which has never been encountered for training by the ANN before. And this happens typically in these steps. First, you feed this unknown data or new data into the input layer of the neuron. Second, there is only feed forward propagation. The data only flows through the network layer by layer, and this process continues until the data reaches the final output layer. Remember, there is no question of backpropagation because now you are not training the network. So you are not really trying to adjust the weights. That process is already completed. And finally, when we look at the output layer produces a prediction or a decision based on the processed input. The nature of this output depends on what was the task the network was trained for. So for example, in this case, it was classification. And we can see that when we feed an image of a dog that the network has never seen, the image goes through feed forward propagation of the trained neural network, and at the output, the model assigns probabilities. As you can see, the probability for it detecting a cat is 0.01, for a dog is 0.98, and for others is 0.01. This is the process of inference, where using the trained model, you classify fresh inputs without making any further weight updates. Next, we understand what is the meaning of accuracy of a particular neural network. So the accuracy of neural network is the number of correct predictions that it is able to make versus the total predictions multiplied by 100%. So please understand, the accuracy of neural network is not this 0.98 which it is doing for just one unseen data. What you essentially do is you show it a batch of dog images, you show it batch of cat images and a batch of human images, and you try to check for this unseen data what is the fraction of images that it is able to classify accurately. And this definition of classification accuracy also helps us to classify the performance of different neural networks for the same task. So I'm giving an example here. As you can see, on the x-axis, we have something called epochs. This is the first time I'm introducing the term epochs. The meaning of epoch is that how many times the trained data has been passed through the network. An example of epoch would be, suppose I have 100 training data images. I divide them into 10 batches of 10. So the first epoch, you train it with 10 images. The next epoch, you send in 10 more images, so on and so forth. What we do parallelly is we check the accuracy of the network to unseen data after each and every epoch. It is natural to expect that as I train the neural network more and more, the accuracy will increase, and then after a while it will saturate. So when we do this for different neural network architectures for the same task, we get an idea of how good the neural network is able to perform in that particular application. So if you look at the curves over here, you see that Linnet A and B, which are your red and cyan curves, quickly rise in accuracy and stabilize to above 80%. That means during inference, these models will give very reliable and high quality predictions. But if you look at AlexNet and GoogleNet, which is represented by green and gray color respectively, you see that it takes many more epochs to reach 70% accuracy, which is still decent, but which is less efficient as compared to your Linnet. And finally, we see the example of SqueezeNet, which is not a very good network for this particular application, that lags behind and plateaus to around 60%, but takes many more epochs to even reach that 60%, which tells us that its inference accuracy will be weaker. Furthermore, there is another very important use of looking at the accuracy percentage of neural networks. It is to understand how your artificial neural network is training, as you can see in this set of images. Let me unpack it for you. Let's look at the left plot first. The blue curve shows you the training accuracy, which is steadily increasing as the network fits the training data, whereas the orange curve shows the validation accuracy, which tells us how well the model generalizes to unseen data. Ideally, both of them should rise together and they should stabilize at a high value such that both are not very different from each other. But as you can see in this particular figure, sometimes it so happens that a gap starts forming between the training and the validation accuracy. If validation accuracy is very close to training accuracy, we have very little overfitting. We will define what that is. But if the validation accuracy stops improving or even substantially reduces with number of epochs, this is a very clear sign of overfitting. So what is the meaning of overfitting? The meaning of overfitting essentially is that your neural network has stopped generalizing data, but it has started memorizing data. A very good example I give in class is rote learning that students sometimes do versus understanding the concepts. If you just memorize, rote learning will not help you do very well in your exams because you are just remembering the formulas and some specific patterns. Slightly you change the question, you will not be able to do well. Only people who generalize and can understand the underlying concepts will be able to do well in the exam. And that is what you see even in artificial neural networks. Okay, with this, we are in a good stage to conclude our study of generic artificial neural networks, and we will next discuss the different kind of DNN architectures that are commonly used for doing several classification operations. So when we talk about neural networks, we are not just talking about one single architecture. Over the years, your researchers have developed a variety of designs, each specialized for a different kind of problem. And you can think of them as different tools in a toolbox. You wouldn't really use a hammer when you need a screwdriver. So in the same way, different architectures or different topologies of neural networks are better suited for vision, language, or even generating new data. So in this context, let's walk through the most important ones. The first one is the one which we have been studying throughout. It is your simple feed-forward neural network. In a feed-forward neural network, information, as you can see, is only flowing in one direction, from the input through the hidden layers to the output. There are no loops or feedbacks. And because of that, these are often called multi-layer perceptrons or MLPs. They are the fundamental building blocks of neural networks, and they are very efficient and very good for solving simple classification tasks and regression analysis when the data does not have any special structures or any special features. For example, if I give you a data set of house prices in Hyderabad based on features like size, location and number of rooms, and MLP can be easily trained to predict a particular price for a new home that is developed in a new locality with suppose 3 or 2 bedrooms. Next, let's move to convolution neural networks, which completely revolutionized the area of computer vision. Instead of connecting every input to every neuron in the next level, CNNs uses a new concept called filters or kernels that slide or convolve across the image. These filters or kernels pick out specific features. It could be a horizontal edge, some texture, or even curve. And as you go deeper and deeper using different kernels and across different layers, the network combines these features into shapes and then eventually into full objects. For example, a CNN may first detect the outline of a ear, then combine it with other features such as the nose or the mouth, and then understand that this belongs to a cat and not a human being. This approach is much more efficient in terms of parameter space than fully collected layers because it reuses the same kind of filters across the whole image. And this is why CNNs are really dominating tasks like image classification, edge detection, object classification, and even self-driving cars. The very popular CNNs which you may have heard of are AlexNet, VGG, and ResNet. Don't worry, we will go into details of CNNs in the next class. The next is recurrent neural networks, where CNNs are very good for images, but what about sequential data? Data that comes in a particular order, like sentences, speech, or text. That is where your recurrent neural networks or RNNs are really very important. Unlike just feed-forward networks, RNNs use loops. You see these loops that allow information from one step to feed into the previous step. And therefore, in other words, they have some form of memory. To understand RNNs, let's take an example in language modeling. So if I say the cat sat on the, you would expect the next word to be mat or table because of the earlier context. Now RNNs can capture this context owing to these feedback loops. However, plain vanilla RNNs struggle with very large sentences because they tend to forget very distant information. To fix this, we use advanced versions of RNNs such as LSTMs, which are an acronym for long short term memory, or even GRUs, which are gated recurrent units, which adds gates to control what information gets remembered or what information is forgotten. And these are still very widely used in speech recognition, in machine translation, and time series prediction. The next neural network we will talk about is generative adversarial networks, which not only recognize data or do classification, but they actually create the data also. So let us look here at the example of a generative adversarial network or GAN. So as you can see here, at the heart of GAN are two neural networks which compete with each other. The first is the generator, which is also a multi-layer neural network, and the discriminator. The generator takes in random noise and produces fake samples, say images that look like pictures of faces. On the other side, the discriminator sees both real samples which come from the training data and fake samples which come from the generator. The job of the discriminator is to tell whether a given sample is real or fake. Now, here is the interesting part. The generator is trained to fool the discriminator, while the discriminator is trained to catch the generator's fakes. And this competition between the generator and the discriminator is what helps to improve the network. If the discriminator correctly spots a fake, it updates its weights and gets even better. But if the generator's fakes get caught, then it updates its own weights to create more and more convincing fake images. This back and forth is repeatedly done through many iterations, and over time the generator becomes so powerful that it can start creating images which are highly realistic. Why images? Even sounds or text, all from random noise. So in essence, the generator and the discriminator compete in a game, and over time the generator gets so good that it can produce faces, paintings, and even videos that look almost real. This GAN technology is what is behind all this AI generated art and deepfakes that you see today. The final DNN architecture, which has revolutionized AI/ML computing, is your transformer architecture. In the transformer architecture, generally at the backbone, you have something like a convolution neural network or any other ANN that is applied to the neural network to extract certain features. If it is image is the input, then it is convolution neural network. To give the neural network information about where each of the features comes from, and also it adds some positional encoding. What happens is, the next step is these features are then passed on into the transformer encoder. What does this transformer encoder do? It uses a special technique called self-attention to look at the relationship between the features extracted from different parts of the image, or in other words, each feature can attend to all other features, helping the model to capture long range of dependencies that a CNN alone would find it very difficult to do. Next comes the transformer decoder, and the objective of the transformer decoder is that instead of scanning the whole image region by region, the decoder works with fixed set of object queries, where each query is essentially a learnable embedding that asks, is there an object here? And if so, what is it? And through this attention to different parts or different features of the image, the decoder matches the queries to the encoded features from the image. And finally, the output of the decoder goes to the prediction head, which essentially goes and does the prediction. And the beauty of all this design is that the transformer keeps reformulating object detection as a direct set prediction problem. That means it generalizes not just for a set of subclass, but it keeps learning on its own. So instead of relying on very complex post-processing, it predicts objects directly with an end-to-end fashion. Okay, so with this, we will conclude today's class. In the next session, since this is very difficult to go into details of each and every neural network, we will pick one neural network, and that is your convolution neural network. We do this because CNNs are conceptually much simpler, and they have become pervasive in computer vision tasks like image recognition and object detection. The study of CNNs will also give us a sense of how complex computations have become and the number of parameters that are used in making even simple classification in modern day neural networks. An example of the same is that the transformer models which go into your ChatGPT, GPT-3 is the third version of your general purpose transformer, has almost 12.5 billion parameters. Now 12.5 billion parameters is more than the number of neurons in a human brain. Number of neurons in a human brain is roughly 9 billion. So it looks like your GPT model is becoming more complex as compared to even the human brain. Okay, let us conclude today's class with this, and in the next class, we will look in detail the convolution neural network. Thank you for your attention. See you in the next class.